This is Math 1340, and this video is over section 2.2, and it's the second part of it. We are going to look at symmetry, and then we're going to finish with the difference quotient, which is something that's really extremely important when we get to calculus, if you get to calculus, or if you go that far. All right, so symmetry, we want to look at if something is symmetrical with respect to the x-axis, y-axis, and the origin, and what it means. To be symmetrical to the x-axis or the y-axis means you're kind of being mirrored onto the other side. And then to be symmetrical to the origin means you're being mirrored across the origin. So the origin itself, or y equals x, that line acts as a mirror. And the way we can do this is to see what happens when we replace our variables with a negative of the variable to see if it just switches signs or not. So we're going to start with looking at something that's symmetric across the x-axis. And so if you look on this graph here, that has, it's kind of like a sideways parabola. If an x value is picked, then the y values are negative y and y based on that x value. That's the indication that it's symmetrical with respect to the x-axis, that there's a negative y and there's a positive y on both sides that this function goes through. Usually it means that you'll have a y squared or a y to the fourth power, something that's even, be symmetrical here. And if we replace y with negative y, you square it, you end up with y squared equals x. Okay, that's the test. You put in the negative value of the y. This is only the test for the symmetrical to the x-axis. Put in the negative value for y, and if it gives you the exact same equation, then it's symmetrical to the x-axis. And that's because that y has been squaring out any negative. So in this, if x is 9, y would be, this is 9, do it this way, y squared equals 9, then y is going to be square root of 9, which would be plus or minus 3. Okay, so you get 3, negative 3. Right. So that's the algebra test for it, is to plug in, start with your y squared equals x, plug in your negative value equals x, and then square it and simplify, so you get y squared equals x. So take the original, replace y with negative y, simplify, and if your result is the original equation, then equation is symmetrical to x-axis. Okay. What's symmetrical to the y-axis is very similar, but we do x instead of the y. So we look at this picture of a parabola. We look at 5. When y is 5, we have two values for x, negative x and a positive x. So we take this y equals x squared plus 1, and we set y equal to 5. Solve for x. 4 equals x squared. So x equals 2 or negative 2. And that's the indication that this is symmetrical to the y-axis. Algebraically, what we can do is take the original, replace x with negative x, simplify, and so you get y equals x squared plus 1. Okay. If result is original equation, then that equation is symmetrical to y-axis. Okay. Now, when it comes to the origin, okay, we're looking at this as the y equals x being a mirror kind of thing in a sense. It's symmetrical across the y-axis or the origin itself. It's kind of like a double mirror. So y equals negative x is also kind of the mirror that kind of shifts it twice. So here, if we have 3 and y is square root of 5, and we'll have negative 3 and y is the negative square root of 5. You have 4, y is negative square root of 12. The negative 4 will be square root of 12. So the points line up across the origin. The test for this is very similar. Take the original. X squared equals y squared plus 4. Replace x and y with negative x and negative y, where negative x squared equals negative y squared plus 4. Then simplify. We get x squared equals y squared plus 4. And then again, if result is symmetrical, or if result is original equation, then the equation is symmetrical to origin. One of the key things with these is when you're looking at your equation, if you have just x squared, just x to the fourth, any x to the even power, you're looking at something symmetrical to the y-axis. If you have just a y squared, then you're looking at something symmetrical to the x-axis, or any y to any even power is symmetrical to the y-axis, as long as that's the only ones left, like the only powers there that are even. So, for example, just go through a couple different ones. If we have 2x squared plus x plus 4, or this is minus 4, y equals that. You have an even and you have an odd power. This is not going to be symmetrical. Okay. If we have 2x squared plus 8, now the constant will be considered even power. The 2 is also even. That should be symmetrical to the y-axis. If we have y equals 2x cubed minus x, you have two odd powers. They should be symmetrical to the x-axis. And if you have y squared equals x to the fourth plus x squared, well, now we have even powers for both y and x. So it should be symmetrical to the origin. So that's what it means by even functions, odd functions. Even functions are symmetrical to the y-axis, odd functions are symmetrical to the origin. And what it means is all powers odd and all powers even. Constant would not be an odd power either. So if we have something like x cubed plus 8, that is not going to be symmetrical to the origin because of that 8. All right, so now we're going to look at the difference quotient. And then this is going to be the last thing for this video. Difference quotient is basically looking at a secant line that connects 2 points out on a curve, and it is a way to kind of um, estimate the slope of the curve by finding the slope of the secant line. So if we are looking at this as x1, y1 on that point, and x2, y2 on this point, then your slope is y2 minus y1 over x2 minus x1. What we can do is we can relabel these. The y here, we can label that y2 as f x plus h. We can label y1 as f of x. Okay. So h is basically just this difference between your y's. Okay. And so we can write this then, y2 is f of x plus h minus f of x. And this would be over x plus h minus, sorry, the h is not your y. H is your x. Difference between the x's. So x plus h, x1 plus h. No, x plus h. x1 is going to be x plus h minus x. So x2 becomes x plus h, and x1 is x. I sure said that before. Where again, the difference between x and x plus h is h. And then this becomes f of x plus h minus f of x. That is your difference in your y's. Over x plus h minus x, which is just h. So that's the difference quotient right there. It's the difference between your y's, your f of x plus h minus f of x divided by h. Now, the main point of doing this is to get h out of the denominator. And the reason why is eventually when you get into calculus, you let h go to 0, and you can't divide by 0. So we need h to be kind of gone from this. So it's not in the denominator. So if when we make h 0, we don't divide by h. We don't divide by 0. But good thing is if we do all the math right, these things work out pretty simply in a sense, but they can take a lot of work still. Even though they work out just right, they do take some work. All right, so let's look at the function 3x minus 2. We have the points, we'll have point x, we'll have point x plus h. So we'll have x, 3x minus 2 is your function, and 3 times x plus h. Minus 2 is your other function, or your other point for x plus h. And so we have the difference quotient is 3 times x plus h minus 2 minus 3x minus 2 for h. What we do is we have to simplify the numerator. So this would be 3x plus 3h minus 2 minus 3x plus 2 for h. Now, the first thing, anything on your right side, anything that's part of your original f of x function should cancel. That negative 3x cancels with this 3x. That 2 cancels with that negative 2. It doesn't happen, there's an issue. Then we have what's left. 3h over h. The h's divide out, we get 3. That is your difference quotient for this, is 3. And the difference quotient really is a slope equation. In this case, we get 3, and what's the slope of 3x minus 2? It's 3. That's how it changes. All right, so h of x equals x squared minus 5. So the difference quotient will be x plus h squared minus 5 minus x squared minus 5 over h. So we simplify the top, we'll multiply out the x plus h squared. So we have x squared plus 2xh plus h squared minus 5 minus x squared plus 5. That would be over h. And you know what? I don't need these parentheses. Write that too. All right, so we cancel what can cancel. X squared cancels with x squared. 5 cancels with 5. We end up getting 2xh plus h squared for h. The h's cancel. Just to kind of show this and separate them out. So we get 2x plus h. Now it's okay that we have the h in the numerator here. If that is 0, then you get just 2x. And you know that we're looking for a function there. The main thing was getting this h out of this numerator, the denominator, so we don't divide by 0. Next one, g of x equals 1 over 2x. We have 1 over 2x plus h minus 1 over 2x for h. This one's a little tricky. What we have to do is we gotta get a common denominator. So we'll multiply the fraction on the left by x. We have x over 2x times x plus h. And the fraction on the right will multiply by x plus h. We have 2x times x plus h. So we're really multiplying it by 1. X over x on the left, x plus h over x plus h on the right. And then we can write this under one denominator. So we have x minus x plus h over the h will go to the denominator as well. So we have h is 2x times x plus h. And then this will be equal to x minus h over 2hx times x plus h. That was just bothering me that they were out of order. X's cancel, you get negative h over 2hx x plus h. And then we get negative 1 over 2x times x plus h. Okay. Now, we still have an h in the denominator, but in this case, if h is 0, that doesn't cause us to have 0 in the denominator. That causes us to have 2x squared in the denominator, which is allowed. You can have a function in the denominator. It changes your domain, but you can still have that. Right, so this is complete. In the next few sections, we'll go more into linear functions and slope. And I'll see you then.